So as I was saying that the limit properties go through some stuff that's gonna be helpful for us as far as evaluating the limit. So this first one's like, hey, if I have a limit, all I have is a constant term. The constant value is the value of the limit, okay? Another one, nice one that you'll see here is dealing with powers. All right, you'll see they also put radicals here because if you remember, a radical can also be written as a rational exponent. So as you deal with exponents involved, this is a nice one because we deal with like exponential functions, right? These are different things that we could possibly start considering as we deal with them, okay? Sum and difference, product and quotient ones will also be some properties that are helpful for us as we deal with these. All right, make sure you see basically if we have terms involved or two functions being added or subtracted one another, we can break it up to the limit of each one separately. Okay, just kind of helps make things a little bit nicer. The same thing is true for multiplication and division. Now, make sure you're careful with that. The quotient, as they're looking here, when it says that you can't have zero in the denominator, right? Remember that was kind of when we looked at that two different results. You can get an undefined result where you have a value in the numerator and zero in the denominator, so it doesn't help us much. Or an indeterminate form. That was another one that we looked at that, hey, we might have to try something else to deal with that, okay? You also see they add what they call a constant multiple. If you go from L4 here, they're calling it, when you look at this property of limits here, if one of them is a constant value, we can take the first one that we just looked at and just multiply by the limit of the other, okay? Things that you probably can see that we've already kind of dealt with by trying direct substitution, but it's bringing to us something that kind of a little bit better way of explaining why it can work the way it does. If those properties were not in place, direct substitution wouldn't be an option for us. Okay, so it is important to know those properties. So I have three problems here for us to start with. I know I went through quick, like I said, I just pulled that straight out of the book. Okay, so that is something that you can find in there. The old edition was page 110, but it's in the differentiation section of the book, okay? With that said, then, if you saw the limit as x approaches 5 is equal of pi, sorry, how would we handle that? Pi is a constant, right? That's not a variable, right? Pi is a constant value that we often think of as the rounded 3.14, right? So understand when you see this, hey, that's a constant value, not quote. That equals pi. Now, we won't run into pi much in this course. That's more like if you had to take trig and go beyond that. Now, if we ever talk about a circle or something, okay, what's the area of a circle? Pi r squared, right? So we might have to deal with it at some point. Like if we're dealing with circles or something, then the same thing for circumference. The circumference of a circle is 2 pi times the radius. So those are ways that, yeah, we might run into pi here, but not as much as, let's say, we're taking trig into perspective, right? So that's one of the main things I get when you wonder about this course compared to our 5-hour calculus course. We don't go over the trig functions that they do, right? So we don't run into pi, but if we had a circle, we might need to use it at some point, okay? But you'll find sometimes we just use the pi button on our calculator or just remember 3.14, okay? But it is a constant. Another constant value that you may have seen before, Euler's constant, right? E. So know that as we deal with this and we go through this course, this is definitely one of the ones that we're going to work with because that's directly connected to exponential situations, okay? Any concerns with constant values there? All right, so the next one, we kind of looked at this already, and I talked about how this would be a good situation for direct substitution. The one thing I would point out here is make sure you see that as I look at this, this is a quadratic expression that we're working with, right? The way I explained it was before that, like, hey, we can have confidence that this is going to be okay as far as continuity because the domain of a quadratic is all real numbers. So we were kind of taking that perspective and, hey, direct substitution, we should be safe here. Okay. The properties here, what I would do is just say, give yourself a little bit more space and go through and start writing it out. So we would say like, hey, the limit as x approaches -2 of the very first term. All we're going to look at is the very first term. Okay. Well, remember, as we looked at our properties, we can look at it this way. The 3 is just a constant multiple, what we call a coefficient. So I can bring that outside the limit. What else did I bring outside the limit? The exponent, right? So in the end, we're just focused on the x, meaning the next term will just be minus the limit as x approaches -2 of x. And then plus the limit as x approaches -2 of 11. Hopefully what you see here, though, this is what leads to a more theoretical perspective, right? If we had to provide a proof of why we can do direct substitution, this would be the reasoning behind it. If we go look at the expression of just x, well, as x approaches -2, what will that limit approach? Approach -2, right? Because that's our whole focus, right? X approaching -2 of x, right? So that's going to approach -2. This one will approach -2. Okay. What does this one approach again? 11, right? Because it's just a constant one, right? But the idea, hopefully you see the connection. This is providing a proof to why we can do direct substitution. Okay, if we didn't have this, we couldn't use direct substitution. Now, are we going to do this every single time we do a limit? Did I do this on Wednesday? No, right? Now, understand that if I put this on the test, and it's one of the ones that sometimes gets brought up on the final exam, as I've noticed. If it says to use the property of limits, it's just wanting to make sure you understand that, hey, I can go and break this down this way. Everyone follow me on that? But if I just say evaluate the limit, direct substitution is allowed because of these. Everyone kind of see where I'm pulling this in from? With that said, though, hopefully you see by plugging that in, we would get what, 12 plus 2? My brain is not working. Y'all, was it 25? Is that what y'all got? Be careful with that -2 in the middle. So the -2 squared is +4. Ooh, times 3 is 12. This becomes +2, so that's where I got 14 from, and then the 11 here, where I got 25 from. I know I'm writing it differently than we did before, right? Hopefully what you're hearing from me, though, the purpose of it is to set in place of why we're allowed to do this. We need this foundation before we move forward, okay? This will be one of those situations that I would point out, like if this was the 5-hour class and we had more time, we would spend more time going through the properties and explaining these things, right? But for me, in my perspective, what I want you to see is like, hey, I'm showing you direct substitution, not just because I want to, but because we're allowed to. Everyone good, though, on the second one here? With that said, we can rewrite the next one the same way. The key here that you want to be careful of is, can I actually put the 3 inside the square root? Okay, so those are always things that we're going to want to watch for. But what you'll find here through a quick perspective, we know that we can rewrite this as such if we wanted to. Not that we have to write it this way, but that's something that we could do. Right, I didn't put it on the 4 this time because I think we're good with seeing that's a constant term, right? So the limit as x approaches anything of 4 is just gonna be 4. So the only thing we need to look at is what happens to x as we approach 3? Well, hey, it approaches 3, right? Just make sure you see here the direct substitution approach would have covered that for us. Okay.
So what would be like the advantage of writing it that way?
It's more about providing a mathematically sound proof to what we're doing. Okay, that would be where it boils down to. It's like using the quadratic formula. If I told you you have to show me where you got that from every single time. Because the quadratic formula wasn't just something that poofed out of nowhere, right? I don't think I covered that in class, but if you complete the square, I think I still have it up. Let's just pull it up. Yeah, so if you have just a general quadratic equation and you keep A, B, and C instead of numbers and you solve for X, you can use completing the square that even though it's A, B, and C involved, we can still get X by itself is the key. Well, when you're done, you get the quadratic formula. Would you want to have to do that every single time though, just to use the quadratic formula? That would get pretty tedious, right? So please keep that would be where I point to like, hey, we have these properties that are important for what we need, but it's not something that we want to have to write out every single time. Okay. Sometimes though, like what I would point to is like paying attention to some of them, like here, these might be helpful to remember that, hey, I can look at these separately. I don't have to look at it as one big picture, but I can look at it separately. That could also be helpful as well. Okay. One of the things as we get through the limits, we're going to be able to define what we call derivatives. Okay. We're not to derivatives yet because we're talking about limits, but as we get there, once we define derivatives, we can start connecting the two, and that'll give us another way to deal with some of the limits that specifically like indeterminate forms. So being able to do this will help us connect it to those indeterminate forms. Okay. Any questions with these though before we look at another one? Hmm. All right, so as we look at this next one here, it says use the limit properties. We're just trying to find the following limits. I didn't mean to put the properties on this one. We're just trying to evaluate the following limit. I just copied, not thinking about it. Sorry, y'all. With the limit stuff in place, though, those properties, we know we can look at the numerator and denominator separately, right? We don't have to look at it as one big picture. So like as we look at the numerator, what is the square root of 25? And then minus 5 is 0, right? And this is us just using those properties to help us with that. And then 25 minus 25, would we all agree is 0? What happens here? Huh? What do we call this? That's an important part here we have to recognize. Apparently I spelled that wrong. Indeterminate form. This is our indeterminate form. Right? We can't make any conclusion off of this when it's 0 over 0. Okay. Now, if you remember, this was something that we looked at before. Where we had this situation involved. Anytime we have a rational, we can try to factor to see if we can simplify. I'm pretty sure we did one with a limit. Here we go. This is where I used it to help show the limits, right? That, hey, I can't plug 3 here in this situation. It wouldn't work. Okay. Where once I do some simplification, then I'm able to get here. Right. So with that simplification in mind, the problem we're dealing with here, we got to look at it a little bit differently. I can't factor this. We have a radical, not a polynomial, excuse me. Now, I show this one in class just to make sure to kind of prepare you that, hey, there are other things that you might have to do from time to time. Remember before, if we have exponents on our variables, try factoring to see if it simplifies. Okay, but no, here's like, hey, I can't do anything with it the way it is. Okay. What's one thing you can do if you get stuck to help try to evaluate this when direct substitution doesn't work? Table method, right? Just remember table method. Go say that, hey, I'm going to look at this as the limit as x approaches 25 from the left and build your table. And then do the same thing from the right, build your table. Now that method's going to take a little work, right? Because you're going to have to go plug in, I would say good 3 values on both sides to show what's going on. I would plug in 24, 24.5, 24.9, and that might help you, right? If you need more, figure it out later. Do the same thing on the other side, 26, 25.5, 25.1. What's going on? If you need more information, get closer to 25. So a table approach is good. Just know that that can be a little tedious sometimes, okay? Now, the good news is whenever you're dealing with radicals, there's also other ways to deal with this. What do we call this situation? If you saw something like a squared minus b squared, what do we call that expression? Give it a special name. Equation. It's not an equation. There's no equal sign. It is a binomial, right? Both terms are what? There's a difference, right? The subtraction there is a difference. What did I put on both terms though? Specifically what? Squares, right? It's a difference of squares. Remember, a difference of squares, we get to factoring because we can get to this place here. Okay, when we see a squared minus b squared or subtraction in both terms are perfect squares, I can factor this. Well, I don't have exponents right now, so I'm not thinking of it from a factoring perspective. But another way to look at these sometimes is kind of like a conjugate pair, right? That's more used with, specific situations. But the idea is that, hey, if I get this pair of factors and I do the multiplication, I will get both terms to be squared. Well, why do I like squared? Okay, well, what is the square root of x squared equal? It's just x, right? If I can get there, I don't even have to worry about the square root anymore. Maybe it'll help me out. That's what we hope to see here, okay? Well, let's do the work and find out what happens. So with this one here, since it's in the indeterminate form, that just means to me like, hey, the properties and direct substitution aren't helping me here, so I need to take another perspective, okay? The table approach definitely will work. Just know that this one might involve a little bit more work depending on the result we get, right? Another great approach though is to say, hey, I have a fraction here. So let me try using my simplifying skills to work with that. So what I'll say to do here is look at these both as a single factor and then multiply by another factor. Just know when you're doing this, the piece that we're focused on is that square root. We want that to be squared. So we're going to say, hey, let's force this to be a difference of squares. So I took the factor I had, the square root of x minus 5, and what did I put? The square root of x plus 5. Everyone agree with that? The reason we like this is now you could go through and FOIL this, right? If you wanted to, you could definitely FOIL it. But what I tell you, only look at the top and realize you're forcing it to look like this. Okay, the one perspective that I hope that you take from your college algebra class is that, hey, with some review, I need to make sure I'm comfortable with this statement, that both of those are equivalent. One's in a simplified form, one of them's in a factored form. Here, I brought in the factored form to help me. The way that it helps me though is now I can write my limit as x approaches 25 as the square root of x squared minus 5 squared all over, and just keep these as factors. Don't worry about multiplying this out. Okay, if we need to, we'll deal with it later, but we'll see what happens. Now, as I mentioned with the rational before, not every limit's going to require this, okay? So please keep that in mind. This is like, oh, hey, I have a square root, even a cube root might come into play, right? Just kind of try to remember these types of factoring formula, sorry. You have the difference of squares. With cubes, you have the sum of difference of cubes. Those are definitely formulas that it would be helpful to remember. Now, hopefully you heard from before I started doing this. If you ever forget these factoring formulas, if I'm just telling you to evaluate this, do you think I care if you do a table? No. Now, I might take off half a point at the end out of 5 points, because if you give me a rounded decimal value when it was supposed to be an exact value, that's the only problem we run into, right? But if it's out of 5 points, 4.5 out of 5 is still what percent? It's still 90%, right? Is everyone clear on that? It's better to get 90% than skip a problem because you don't remember how to factor it like this or use this strategy. Is that clear to everyone? Just know that like, hey, it might take me a little while to have to plug in all those numbers. So do you need help with your calculators again? Make sure you talk to me. I'm always in here before class over in the math lab. So this would be a great time to take advantage of that. Now, starting on September 26th, I'll have a class before y'all in here. So I won't be available at 10, but from 8:30 to 10, I will be in the math lab right here. Okay, so if you need help with your calculator, as mentioned, some of them you could plug it in and just keep letting it do the evaluating for you. Okay. With that said, though, this limit now can be simplified. As x minus 25 all over x minus 25 times the square root of x plus 5. What do we like about that? Right? Yeah, it can simplify, right? Not always going to happen, right? Please understand that this is just, hey, I see a square. Let me see what happens. Maybe this will help me. Okay. As I mentioned, though, that's not always going to help me. So once we get from limits and we start talking about differentiation, we'll be able to connect the two so that if this doesn't work out nicely, we might be able to try a different perspective. Okay. But what hopefully you see here is I was able to manipulate this. It's not really simplifying. It was more just kind of changing how it looks. But now we can simplify, right? And the reason we like that is the factor with the subtraction is gone. That was one issue that we're working with, that zero in the denominator. Without the zero in the denominator, now we have something we can work with. Okay, just be careful to see here, there's a 1 in the numerator when you do this. So that when I plug this in, I'm going to have 1 in the numerator. And then down here, we will get what, 10? Which hopefully you see from a table approach, you might be able to get 1/10 from that. Does everyone kind of see how that would be nice from a table approach as well? The issue is like, say your answer was a square root of 2. Table approach, you're not necessarily going to get an exact answer for square root of 2 because all you're going to be able to do is round it. But I think from a table, you might eventually get to, oh, it might just be 0.1. Okay. Any questions or concerns here though with this one? Yep. Well, the top one tells me I couldn't do direct substitution right away. So that would be like step one. Try direct substitution. Hey, this didn't work. Right? I would encourage you to write out something along the lines that makes it known that you recognize it's the indeterminate form. Because of that, I'm trying something different. So that's kind of like, oh, I got something that I need to recognize that leads me to do something else. That's what that does. Okay.
Is there no instance where the answer would be like it's undetermined or like it's?
But if the zero's left in the denominator, remember that would be a undefined situation. What you'll find is typically with the indeterminate form, it leads us to try other stuff usually. Okay.
Would you like try this if you're still getting 0 in the denominator? Like
Then
your
we,
answer
yeah.
would be indeterminate.
Mhm.
Okay.
So like, for instance, like, you know how I gave us the graph? I had it as x squared minus 9 over, what was it, x minus 3? We were able to factor and simplify. Well, what if I make this x minus 3 squared? Right now, the way it is, I plug 3 in the top, I get 9 minus 9. Plug 3 in the numerator, I get 3 minus 3. There's 0 over 0, indeterminate. But if we factor the numerator and then simplify, we would have this. Because I put one more factor in the denominator, we're still going to have a 0 in the denominator. So that would be an instance where like, hey, I got the indeterminate form. So I factored the expression, I simplified the expression. Well, guess what? I still can't do anything with it because I get a 0 in the denominator. Okay. And as we talk about this, I'm going to do a little bit more of the limits of infinity involved. That was one thing that we looked at yesterday as we finished up. Right. It could be that the limit doesn't exist. So this would be a situation where hey, now that we know what kind to expect, let's take the table approach. So whenever you get a zero in the denominator, but had a value in the numerator, do the table approach before you say does not exist. The reason being is we said this one didn't exist because of what? Well, not just because it's infinity, but one side was negative infinity, the other side was positive infinity. Are those the same? No, so we have to be careful because there might be a situation where we could say infinity or negative infinity because they're both the same, which, we still have to dig into that, of course. Infinity is one of those ones that kind of leaves a little bit of uncertainty on how to handle it, okay? Does that help with that? It is kind of tough to see everything because I had to make sure I grabbed the problem that this worked nice, right? So if I wasn't careful, then we would have been stuck and had to go to the table approach, okay? Other questions or concerns? All right. So the next thing I want to do is just kind of continue with doing our limits. All right, what I want you to see here, all right, is what happens when we start looking at the far edges of a function. For those of you who recently took college algebra, you will remember this from the perspective of end behavior, right hand or left hand, as far as end behavior is concerned, okay? Now, as we deal with this, there's some things that are nice to work with and some things that are going to involve a little bit more. I'm going to do some tables with the second pair to help us see it, but the first two, hey, we can definitely deal with this. This is something that we're capable of. All right. Now, as far as dealing with this, if I give myself a little bit of space here, the properties, this would be a situation where I feel the properties would help you better see what's going on. Okay. So looking at this as individual limits, remember that this first term here, I'm just going to put the cube on the outside. Okay. So we'll say the limit as x approaches infinity of x, and just I'm going to cube whatever I get. Okay. And then the next one, I'm going to put -7 on the outside. For the constant term, though, remember, we can just put 9. All right. If you need to put the limit as x approaches infinity of 9 to see it, that's fine. But just remember, it's a constant term. So that I'm just going to get 9. The reason I like to point this out is just to make sure to show you that essentially I'm doing the same thing for both of these, right? What are both of these going to approach then? If you just plug in numbers into x and they keep growing forever to infinity, well, that result is going to be infinity. Everyone agree with that? Now, with that said, if you saw infinity cubed, how would you say, what would you say that would eventually be?
Infinity.
Still infinity, right? So if you saw infinity plus infinity, infinity, I can't write it right now. Plus infinity, what would you say that equals? Still infinity, right? What if I put +9 on there? Still infinity, right? So make sure you see here that as I look at this, because I was focused on x approaching positive infinity, now be careful with that, it is positive. We can just go look at this and say, hey, the right hand is going to approach infinity. Now, for those, again, if you took college algebra releasing, your teacher might have says, hey, it either rises or falls. That would have been like, oh, the graph is going to rise on this side. If we want to go graph this on that side, we need the graph to look like that. If you remember a cubic, though, it follows kind of a pattern similar to that. So if one side rises, what do we expect the other side to do? Fall, right? Anytime you have a polynomial where the degree is odd, the two sides are going to do the opposite, right? That was one of the things you could definitely help like recognize from the beginning. This is how we write that out properly, though, from a mathematics perspective. We didn't have this in college algebra, though, right? We're bringing this in now to say, hey, this is a better way to write this. Okay. Now, with that said, this is definitely a helpful way to quickly kind of look at what's going on with something. As we talked about different perspectives, if you're looking at how something grows and it's following an exponential or logarithmic pattern, we can begin to find, like, say, maybe there's a limit to how much it can grow. Let's look at that. Well, now I have a way to write that. The limit as x approaches positive infinity, right? Now, make sure you see here, though, plugging in the negative infinity will change it up a little bit. Specifically, what we need to look at is what is negative infinity cubed? It's negative infinity, right? So what will this approach then when we take that into consideration? Negative infinity, right? Now make sure you see there, this does look a little weird because that would be negative infinity, this would be positive infinity. But this is where we have to take into consideration, like, hey, a cube will definitely outweigh a linear term, right? This is where we take our knowledge at. If something grows linearly, it's going to do this, where something growing as a cube, it's gonna break away at some point. Everyone follow me on that? So this follows that pattern. So when we compare these two terms, overall, it's going to be negative infinity because of the degree that that polynomial has. Is everyone comfortable with that? Why it's negative? It would have been positive, exactly. Which at that point, remember, squared, then both sides should do the same thing. Right? Now, if we try to do the same thing on the next two, though, what do we run into? Does that help us much? If it was the other way around, right? Infinity divided by two, we just say infinity, right? But make sure you see on these next two, this is where we have to say, all right, hold up, let's look at this from another perspective. Are we okay though with the first one, the cubic example? Give myself more room with these. Now, the good news is when I do the first one here, we'll be able to kind of use that to help us with the second one. Hopefully you saw that on the previous one we looked at here. When I did it with positive infinity, it helps us with negative infinity as well. To help with this though, what I'm going to do is build a table, right? So from the beginning, I get 2 over infinity. I can't make any decisions based on that, right? Like I said, if it was the other way around, infinity over 2, we would just say infinity. But because it's in the denominator, I can't really say anything about it right now. This is where a table will help us better understand though. We could take our expression and say, hey, if I'm going to take values of x and plug it into here, and to see what that pattern looks like as x grows, we can go plug in, say, 5, 100, 2,000. Just picking random numbers, okay? Now, what did I do with my x values here, though? I made a positive and I made sure they're increasing. Now, did I do small steps in increasing or bigger steps? Bigger steps. Remember, if we're approaching a specific x value, we want our steps to get smaller, right? But since we're approaching infinity, we want to see our steps get bigger, okay? So with that said, this is definitely a situation where I want us to be comfortable with our calculator, so make sure that you practice. Just doing it real fast, I plug in 5, we get 2 over 7. We get 2 over 102, 2 over 2002, but really what we want to look at is the decimal here to better understand. So 2 over 7 is about 0.286. The 2 over 102 is 0.0196. And the 2 over 2002 looks something like that. Make sure I do my scientific notation correctly. So the x value is getting bigger, right? What's happening to our output? Decreasing, right? With that said, will it ever become negative?
No,
How do we know here it will not become negative?
it just will, We'll keep giving a positive value larger than zero.
right? How do we know that though? What numbers are we putting in? We're putting in positive numbers. Everyone do understand that? What do we do after we put in that positive number? What's in the denominator? Just plus two, right? If I put in a positive number and I add two to it, the result will always be positive, right? So we know it will never get to negative. Well, what number does this seem to approach then? We know we'll never cross that number, but we won't actually get to it. It approaches zero, right? Now you can pick up numbers. If you want to see more, go put in 10,000, go put in 100,000. What you're going to see, it's only going to increase. When I plugged in the 2,000 in my calculator, it automatically put it to scientific notation with, as you see here, 1, 2, 3, 4, 10 to the negative 4. So we're looking at a number getting really small. If I change this to 10,000 instead of 2,000, it's giving me 1.9 times 10 to the negative 4. May not seem as much as similar, but look, it went from 0.0009 down to 0.0001, even closer to zero now, okay? But will we ever actually get to zero if we started plugging in numbers? No, right? We could plug in numbers, they're just gonna continue to get smaller and smaller. Does everyone follow me on that? What do we say about the limit then? The limit equals zero. And this will be one that we definitely want to kind of watch out for. A table is a great way to discuss that, though. Everyone follow me on that? With that said, if I took this table and I did it with negative infinity, what's going to change? Well, yes, right? Because we're plugging in negative numbers now. Now, there are some exceptions, right? If I plug in -1, -1 plus 2 is 1. But if I plug in -100 and I add 2, the result will still be what?
Negative.
Negative. Everyone agree with that? If I plug in negative 10,000, it's still going to be negative. What you'll find here is all of these will just have a negative sign on. There will be some slight differences, right? Because we're adding 2 to it, so then it's going to change a little bit. But all of those will have negative signs on it. With that said, what is this approach? Still approaches zero. Everyone see that? I encourage you to go do that on your own, though, is copy down the table and just plug in the negatives of what I did and see for yourself that, hey, each of these would come out similar, nice fractions on your calculator. You can make sure you know how to change to decimals. You get a quick look, but you'll see they keep getting closer and closer to zero. Yes, they might be negative, but all you're seeing there is if I look at the x-axis, on the right-hand side, when we consider this, we're approaching like this. But we'll never actually get there. We're on the left-hand side. When I look at this one, we're approaching like this. Okay, but we're still approaching zero. If you remember, again, this is where we call it a horizontal asymptote. This graph has a horizontal asymptote. When I look at the end behavior on the right-hand side and the left-hand side, they both approach zero. So when I go to graph this, I would draw that dotted line at y equals 0 and then make sure two edges go to that without ever crossing it or touching it. Yeah.
Negative, then you get.
Well, I was just saying -1 plus 2 gives you a positive number. But when we go to say now -10, -10 plus 2 is -8. We're looking at the denominator. I was just showing that when we look at these, right, when I go to deal with negative infinity, they may not be the same number, but they'll all be negative now, is the key. You're going to get different numbers. Yes, they are going to change. But remember, we're not focused on plugging in 1 and stopping. We're not focused on plugging in -2 and stopping. Right? We can't even plug in -2, so that wouldn't even be considered in this conversation because -2 would put a 0 in the denominator, right? Really, technically speaking, when you do this table, it's very important that you come over here and say, hey, I'm going to start at -3 because I can't use -2. And then grow from there. -100, -2,000. Okay. -5, like I said, you would have been fine. Okay. If I remember right, we do the Trying to see what we did yesterday. Not yesterday, sorry. This was the same one we looked at on Wednesday, the same function. So this, if I say X approaches -2, this is where we would want to kind of focus on, like you see, I actually have -1 as one of those things we're focused on. To kind of look at that pattern is what happens as I get closer to -2, okay? You'll see on one side that's still one negative, one's positive results. So that's where we got these from. Make sure you understand here, though, we're now approaching infinity. So we need to look at the extreme cases. That's our main concern. We're getting as far to the left or as far to the right as possible. Does that help? Now, fortunately I picked 5 because I should have mentioned like, hey, be careful around -2 because we can't even use that. Okay. Now, what you'll see though, as we talk about limits, we can begin to use this help us with graphing, and I'll bring that a little bit later once we start dealing with differentiation as well. We can show how all this together helps us. Now we know how to get a horizontal asymptote. The other one gave us a vertical asymptote. We can start bringing that together. Okay. The other questions or concerns here? What I hope you see is basically we're looking for, hey, if I don't have any fractions involved, it's probably going to be infinity or negative infinity. The second I bring in a fraction, this is one example where, hey, if the denominator grows without bound, while the numerator remains steady, I'm probably approaching 0. What is it if we get infinity over infinity, though? Indeterminate. Indeterminate. I think that's something I probably should have showed you. Oh, I know we've kind of looked at it more the 0 over 0 spot. I don't remember what page it's on. Let me find it real quick. Well, as they come up, I'll make sure to cover more. So far, this first section only focuses on 0 over 0 for the indeterminate form. Because of more of like, hey, that points me to I could try to simplify. So make sure you see here, this is the main one to watch for. Infinity over infinity, we'll take care of as we move forward, okay? Because you can't base that off of infinity. Infinity is not a number, so we can't use infinity divided. Like even with this situation here, when I'm telling you that infinity cubed plus 7 infinity is still infinity, I'm being sketchy because remember down here, this is technically negative infinity plus infinity. Just what we're doing if we look at them individually. So this is where it's like there's some gray areas here that for our perspective, sometimes I have to say, trust me, right? But based on this, I feel we could have been confident on the behavior of cubic, right? That's why I made sure to draw a little quick sketch to remind us, hey, a cube definitely is going to grow faster than a linear term, right? This one here, I feel this is a good way to actually explain something. You were just told, hey, there's a horizontal asymptote. Now you have a way to show that. Okay. Hopefully what you see here though, if you ever get stuck, a table is always a great way to walk through that. Do the same 2 tables on these first 2, and you'll see the numbers are growing rapidly. Okay, one side will be negative though, of course. Okay, so keep that in mind. Any questions or concerns? All right. Well, I feel that's a good way to cover. Just know that as we go with this, some things to be prepared for. We'll talk more about continuity. This will be where we pick up next week, and then we need to jump into the rates of change. So be ready to use the slope formula when we talk about lines, but also use average rate of change. If you came in after I took roll, make sure you see me. 1 second, what was that?